Real-time kernel. What is real-time kernel? See, kernel of real-time operating system itself, we are calling it as a real-time kernel. And this real-time kernel is highly specialized and it contains only the minimum set of services that are required for running the user applications or tasks. The basic functions of a real-time kernel are task or process management, task or process scheduling, task or process synchronization, error or exception handling, memory management, interrupt handling, and time management. Task or process management. See, this task or process management, it deals with setting up the memory space for the task. Next, once it sets up the memory space for the task, next thing it will do is it will go for loading the task code into the memory space. Once the code is loaded, then it will go for allocating the system resources. Then it will go for setting the task control block for that particular task. Fine. What does this task control board contains? See, this task control block, it's not board, it's block. What it contains? It contains the task ID. That is identification number of the task. Then it will have the task state. Task state means in what state the task is in. That is, the state can be ready, state can be blocked, state can be processed. Ready means it's already loaded into the memory and it's ready for execution. Fine. Block means it's waiting for the IO, some IO job to be completed. So on. Next one is the task type. What kind of task it is? It will go for indicating the type of the task. This task can be a real time or it can be a hard real time task or a soft real time task or a background task. Hard real time task means it is like with the timing is very critical. Timing is very critical. It's a time bound task. Soft real time task means it is with respect to the time, we can say time is not so critical here. Then coming to the next one is the task priority. Task priority, it will go for setting the task priority. If that particular task has got the highest priority, then the task priority will be set to 1. Next is the task context pointer. It is nothing but the pointer for context saving. It will go for saving the context of that particular task. Next is task memory pointers. We have 3 memories here. The code memory, data memory and the stack memory. So we'll have the pointers to the code memory, pointers to the data memory and pointers to the stack memory of the task. Then coming to the task system resource pointers. These pointers will go for pointing to the system resources like semaphores, mutex, etc., which are actually used by the task. Only with respect to that particular task, which system resources are being used, for that we'll have the pointers. Other parameters, it can go for storing the other relevant task parameters. Fine. And these parameters and the implementation of this TCP, it is dependent on the kernel. And this TCP parameters, they vary depending upon the kernel and also based on the task management implementation. This task management services, it will go for making use of the TCP in order to create a TCP for the task on creating a task. It can go for removing or deleting the TCP of the task when the task is terminated or deleted. It will go for reading the TCP to get the state of the task. Then update the TCP with the updated parameter on depending on the need. That is like for context switching. Then it will go for modifying the TCP to change the priority of the task dynamically as and when needed. If the task priority is not like if you have one more task coming with a higher priority, then this task priority can be like this can be switched over and even the task priority also can be changed. Task or process scheduling. See, this task or process scheduling, it will go for dealing with sharing the CPU among different tasks or processes. Sharing of the CPU with respect to different programs. It's a kernel, we have a kernel application called a scheduler. This will go for handling the task scheduling. And the scheduling is nothing but an algorithm, your scheduler is nothing but a algorithm implementation, and it will go for performing efficient and optimal scheduling of tasks in order to provide a deterministic behavior. Coming to task or process synchronization. See here, this task synchronization means if you have two or more programs running concurrently, that is simultaneously, if they are running simultaneously, then there may be an issue like what resource had to be used by what. So this is taken care by the task synchronization process. Fine. Here, what we can define here is, it will go for dealing with synchronizing the concurrent access of the resources which are shared across multiple tasks and the communication between various tasks. So whatever shareable resources are there, how the resources are being shared, and how the task can go for having a communication with respect to sharing of the resources. This is taken care by the task synchronization. Error or exceptional handling. See, this error handling or exceptional handling, it goes for dealing with the registering as well as handling the errors which have occurred or the exceptions which are raised during the execution of task. Examples here are due to insufficient memory, timeout, deadlocks, deadline, deadline missing, bus error, then divide by 0, then unknown instruction executed. These are the few examples. See, this error or exception, it can happen at the kernel level services or at the task level. Deadlock is an example for the kernel level exception, whereas timeout is an example for the task level exception. This OS kernel will go for giving the information about the error in the form of a system call. One example here is get last error. This API, it is provided by the Windows CE or Windows CE. Then embedded compact RTOS is example for such system calls. We have a watchdog timer. Watchdog timer, it's a mechanism for handling the timeout for the tasks. See, certain tasks may involve waiting for the external event from the devices. They need some parameter from the external device. The external device has to send that data. So, the task will go for waiting to receive that data. But what happens if the external device does not respond and it will not go for sending the data? In this case, what is happening here is, tasks have to wait infinitely for the external device if it is not responding. Then, in order to avoid this, what is being done here is, we are going in for using a watchdog timer. See, watchdog, it will be loaded with a maximum expected wait time for the event, and if the event is not happened within that maximum expected wait time, then the same thing is informed to the task. This information is carried to the task and task will be timed out. Fine. Maximum expected wait time is calculated and that will be loaded to the watchdog. Once the timer expires, this will be carried to the task and task will go for having a timeout event. But if the event take place before the timeout, then watchdog timer will be reset.